Welcome to session 3 of Unit 3 in learning the course Design and Analysis of Algorithms. In our previous session, we discussed about an application of dynamic programming, which is nothing but multi-stage graphs. In our today's session, we are going to discuss about another application of dynamic programming, which is nothing but optimal binary search trees. The main objectives of this session are to understand what is optimal binary search tree, to solve optimal binary search tree application by following dynamic programming. The learning outcomes of this session are, by listening this session, one can understand what is optimal binary search tree and able to follow dynamic programming strategy to solve or to develop algorithms to solve optimal binary search tree application. The topics that we are going to discuss in this session are what is binary tree, what is binary search tree, what is optimal binary search tree, what is a problem statement, and what the dynamic programming algorithm we are following, and finally solving an example problem. Coming to binary tree, what is binary tree? What is the definition for binary tree? Let us see. A binary tree is a hierarchical data structure in which each node has at most two children, generally referred as left child and right child. I hope you all know that binary tree. What is binary tree? A hierarchical data structure in which each node has at most two childs. At most two childs. Those two childs are referred as left child and right child. At most two means it may have 0 childs. It may have 0 childs, or it may have 1 child, or it may have 2 childs. More than 2 childs are not possible in case of binary tree. Now let us see here, this is an example for binary tree. Let us see here, this is the root node, and here these are the child nodes or terminal nodes. These are the intermediate nodes. If you observe, this is having 2 childs. This is having 2 childs. This is also having 2 childs. Now this is also having 2 childs. This is having only 1 child, and this is also having only 1 child. And these are not having any childs. This is having 0 childs, this is having 0, this is having 0, and this is having 0 childs. If you observe all the nodes, at most 2 childs are there. So which is to be called as a binary tree. Next, see binary search tree. What is binary search tree? Binary search tree is a node-based binary tree data structure which has the following properties. What are those properties? The left subtree of a node contains only one node with keys lesser than the node's key. Left subtree, that is the values which are present in left subtree are less than the root node. The right subtree of a node contains only nodes with keys greater than node's key. That is, the elements which are present in the right subtree are greater than the root node, and the left and right subtree each must also be a binary search tree. So each left child of root node and right child of root node, those individually they become binary search trees. Now here what is a binary search tree means? It should be a binary tree first. It should be a binary tree. That is, it must have not more than 2 childs, and the properties that are to be satisfied by a binary search tree are left child is less than the root node and right child is greater than the root node, and the left subtree and right subtree should also become binary search trees. And now here you can see an example of binary search tree, and I am saying that binary search tree is efficient one in searching. Why we are considering this binary search tree means its searching process is efficient. If you observe here, if you consider a small array, sorted array, searching the element in a sorted array and searching the element in a binary search tree. If you observe, I am going to search 27. The element 27. If you observe, the sorted array takes 10 steps to search the element 27. But if you observe the binary search tree, it completed the process within 3 steps. Within 3 steps, it completed the process. So it takes 10 steps. So that's why we are saying that the binary search tree is efficient when searching a key element when compared to that of the linear sorted array. Now coming to optimal binary search tree. What is optimal binary search tree? Let us see. An optimal binary search tree, which is also to be called as optimal BST, sometimes called a weight balanced binary tree. The optimal binary search tree is also called as a weight balanced binary tree, is a binary search tree which provides the smallest possible search time or expected search time for a given sequence of accesses. Here, what is optimal binary search tree? The binary search tree which provides the smallest possible search time. That is, suppose for example, here I am giving you a clear explanation for that optimal binary search tree. I have taken 3 key elements. Those key elements are nothing but 10, 20 and 30. Here I taken 3 key elements which are nothing but 10, 20, 30. With these key elements, I can represent a number of binary search tree organizations. Now here this is one binary search tree organization. This is another binary search tree. This is another binary search tree. This is another binary search tree. And this is another binary search tree. Out of these 5 binary search trees, which completes the searching process with less time is called as optimal binary search tree. Here with the same key elements 10, 20 and 30, I can represent 5 binary search tree organizations. Out of all those 5 binary search tree organizations, which gives the search process efficiently or the smallest possible search time, that is called as optimal binary search tree. How to find the search time manually? Let us see the search time, how to find the search time manually. Now here the element 10, here this is present in level 1. The element 20 which is present in level 2. Here this element 30 which is present in level 3. Now here 10 is present in level 1, 20 is present in level 2, 30 is present in level 3. Now we need to find the average value of these 3. 3 plus 2 plus 1 which is nothing but 6. 6 by 3 is 2. The average search time is 2. Now if you observe this one, here this is also in level 1. This is in level 2, this is in level 3. The average value is 2. If you observe this one, this is present in level 1. These 2 nodes are present in level 2. That is 2, 10 is present in level 2, 20 is present in level 1, 30 is present in level 2. The total value is 2 plus 2 plus 1 which is nothing but 5. 5 by 3 whose value is 1.66. Now in the same way, if you observe this one, level 1, level 2, level 3 which gives average value as 2. In this case also, level 1, level 2, level 3, here 1 plus 2 plus 3 which is nothing but 6. 6 by 3 which gives 2. Now out of all these search times, this is having less time, 1.66. Remaining all are having a search time of 2. But this is having a search time of 1.66. So this is called as an optimal binary search tree. An optimal binary search tree. Here we given only 3 elements. With that 3 elements, we can easily found optimal binary search tree by manually drawing all those binary search tree organization and by manually finding the search time. But if you given more than 3 nodes, in that case we will get more number of binary search trees. So it is not possible to find optimal binary search tree within the given limits of time. So that's why we are following dynamic programming to solve that optimal binary search tree problem. Now let us see here what is the problem statement. What is the problem statement that we are going to solve? Here given a fixed set of identifiers. Here identifiers are nothing but elements. Binary tree elements. Those fixed set of identifiers are nothing but A1, A2, A3, so on, AN. The probabilities of tree nodes. Here we also given the probabilities of tree nodes. The probabilities of tree nodes are given as P1, P2, P3, so on, Pn. And dummy probabilities, which are nothing but Q0, Q1, Q2, so on, Qn. Here you can observe the probabilities of tree nodes are represented from P1 to Pn. The probabilities of dummy nodes are represented from Q0 to Qn. That is, one dummy node is extra when compared to that of the given key elements in any binary tree. The optimal binary search tree problem is to construct an optimal binary search tree with the given identifiers. Here we are given some number of identifiers and their probabilities and their dummy probabilities. With the given 3 values, we need to construct an optimal binary search tree. Right. Now here this problem can be solved within the time complexity big O of n power 4. And let us see about the dummy nodes. What are the dummy nodes? Here this is key 2, this is key 1, this is key 4, key 3, key 5. That is how many elements are given for us? 5 elements are given. Here I given 5 elements. Corresponding to 5 elements, I have 5 probabilities. Those 5 probabilities are represented as P1, this is P2, P1, P4, P5, P3. And if you observe, corresponding to this key, we have 2 dummy probabilities, D0, D1. And corresponding to, which are represented with Q0, Q1. And corresponding to this one, we have 2 dummy, which are nothing but Q2, Q3. Here corresponding to this we have 2, which is Q4 and Q5. So always when compared to the key nodes, the dummy nodes are present 1 extra. So that's why we given Q0 to Qn. Right. So by using all these values, we need to find the optimal binary search tree with the given for the given identifiers. Now let us see here manually how to do this process. So if you have given the probabilities, in that case, how to find the optimal binary search tree. Here for example, for simply explaining, I have taken an example which is nothing but, here I given keys 10, 12 and their frequencies as 34 and 50. Suppose if the dummy probabilities are not given, only the key probabilities are given. Here this is first key probability and this is second key probability, and here key elements are 10 and 12. Now here what are the possible search tree organizations, binary search tree organizations? This is one possibility and this is another possibility. Now what about the search time for these two? How to calculate that search time? Here 10 is present in level 1, 12 is present in level 2. What is the probability of searching 10? 34. So 34 into its level. The searching probability of that element into its level. Now, what is the searching probability of 12? 50. 50 into 2, which becomes 134. In the same way, for the second tree. Now, 12 is present in level 1, 10 is present in level 2. What is the probability of 12? 50. 50 into its level, that is 1. What is the probability of 10? 34. 34 into its level, which is nothing but 2, which is having a probability of 118. Now, out of these two, since 118 is small, this tree gives optimal searching process. That tree gives optimal searching time, and this is the optimal binary search tree for that small example. Now let us see if we given the dummy probabilities also. In that case, how to calculate the probability or searching time for the elements for that particular tree. Now here I given the key elements are if and int. Now here the key elements k1 and k2 are if and int. Their probabilities are 3 and 5, and I already said you that if key elements are 2, the dummy probabilities are 3. So 1 is extra. If key elements are n, there are n plus 1 dummy elements, dummy nodes. That's why here the dummy probabilities are 3, which are nothing but Q0, Q1, Q2, which are given as 1 to 5. Let us see the possible tree organizations. Here this is the first tree organization and this is the second tree organization. Let us see. If is the root node, int is its right child, and here this is having a dummy node here, and this is having a dummy node, and this is having a dummy node. In the second case, int is the root node, if is the left child, and these three are the dummy nodes. Now how to calculate the search time? Let us see here. Present in level 1, int is present in level 2, and this dummy node is present in level 2, these dummy nodes are present in level 3. Now how to calculate this one? Let us see first one. Here if, what is its probability? 3. 3 into its level. If is present in level 1, the probability of searching if is 3. So 3 into its level, which is nothing but 1. Next, coming to second level. Now first a dummy node is present. What is the probability of dummy node? 1 into its level, and we have present a key here. The probability of searching int, the key int is 5, and 5 into its level 2. And coming to the next one, the dummy node whose probability is 2 into it is present in level 3, 2 into 3. In the same way, the probability of searching another dummy node is 5 and it is present in level 3, 5 into 3. By calculating all these values, we will get the search time as 30. Now, in the same way, if you take the second one, int whose search probability is 5 into its level 1. Next, if whose search probability is 3 and it is present in level 2, so 3 into 2. Now first the dummy node 1 which is present in level 2, 1 into 2. Here this is the dummy node 2 whose probability is 2 and it is present in level 3, and the dummy node here its probability is 5 and its level is 3, and by simplifying all these values we will get a search time of 34. Now out of these two, the first one is having less search time. So this is optimal binary search tree. So manually we can do easily if we give 2 key elements or 3 key elements, but more than that we cannot do manually, so it takes more time. So that's why we are following algorithm, dynamic programming algorithm, to solve this optimal binary search tree. Directly we can construct an optimal binary search tree for the given key values with their key probabilities and dummy probabilities. Right. Let us see the algorithm for optimal binary search trees. Now here we are passing 3 parameters. The 3 parameters are P, Q, N. Here P are the probabilities of key elements, Q are the dummy probabilities of dummy nodes, and N is number of identifiers. Now given n distinct identifiers A1, A2, so on An, such that A1 less than, A2 less than, so on less than An. So if the given identifiers are not in this order, in the increasing order, you need to arrange them in the increasing order, and their probabilities are Pi and the dummy probabilities are Qi. And here I am going to find C, cost, root, R, and weight of the tree, W, and we are going to find the OBST, which is nothing but T, that is optimal binary search tree T. Now what the procedure that I am following? Let us see. For I is equal to 0 to n minus 1, first I am going to find weight, root, cost. Okay, so for all the values of nodes 0 to n minus 1, I am going to calculate weight, root, cost values, and also I am going to find weight, root, cost values, and here for the last node I am going to find weight, root, cost values, and from there onwards we are going to find the root value, weight value, and cost value for the remaining nodes, and finally we will return the values of weight, cost, and root node of optimal binary search tree. So this algorithm entirely can be better explained by taking an example. Now let us see how to solve this problem. Now here given identifiers do, if, int, while. Here I given 4 identifiers, do, if, int, while, and their probabilities are given as 3, 3, 1, 1, and the dummy probabilities are given as 2, 3, 1, 1, 1. We need to find the optimal binary search tree organization for the given identifiers do, if, int, while. Now here we are going to calculate the weight, root, cost at each and every node, and we are going to tabulate the values. The table should be like this for this problem. Since this is containing 4 identifiers, the size of the table is like this. This process is called as entirely memoization. I already explained while we are talking about dynamic programming general method, memoization. Here I did that tabulation. The size of that table is like this, W00 to W44. Suppose for example if you given 5 key elements, in that case the table size becomes W00 to W55. Here in this case W00 to W04, but if you given 5 key elements, in that case it becomes W00 to W05. So like that you need to calculate. Now here I given some values for all these things, how to calculate all these values and how to tabulate all those values. Let us see how to calculate all these values. Now here given identifiers, and the same example I taken, what the example we taken earlier, the same example I taken. Now I am going to analyze the algorithm for this example. Now let us see what is the algorithm we have for I is equal to 0 to n minus 1. What is n here? N is number of identifiers. What is n here? N is equal to 4. N minus 1 means here 0 to n minus 1. 4 minus 1, which is nothing but 3. 0 to 3. What I need to do? First I value is 0. So here I take 3 values, 4 values, 0, 1, 2, 3. First I am taking I is equal to 0. Now let us see what I need to do. W0, 0 is equal to Q0. What is Q0 value? 2. Now in the same way, R0, 0 is equal to 0. C0, 0 is equal to 0. Now after that, what we have? Wi, I plus 1. I is 0, I plus 1 means 1. 0, 1 is equal to Qn. Qn means 4. Q4. What is Q4? 1. Here Q4 is given as 1. Next, I plus 1. R0, 1 is equal to 0. C0, 1 is equal to 0. For I is equal to 0, I computed that values. Now in the same way, if you take I is equal to 2, in that case, I is equal to 1. In that case, what we are going to compute? W11. What is W11? Q1. What is Q1? 3. R11, which is nothing but 0. C11, which is nothing but 0. Now in the same way, I plus 1. I is 1. I plus 1 means 2. W12 is equal to Q4. Q4 is 1. R12 is equal to 0. C12 is equal to 0. In the same way, if you take I is equal to 2. Now in this case, W22 is equal to Q2. Here what is Q2? 1. R22 is equal to 0. C22 is equal to 0. In the same way, I plus 1, that is 2 plus 1. W23 is equal to Q4, which is 1. R23 is equal to 0. C23 is equal to 0. In the same way, I is equal to 3, the last value of I, 0 to 3. Here we done 0, 1, 2, 3. Now W33 is equal to Q3. What is Q3? 1. R33 is equal to 0. C33 is equal to 0. In the same way, W34, which is equal to Q4. Q4 value is 1. R34, whose value is equal to 0. C34, whose value also is equal to 0. And finally, after the completion of this for loop, what we are doing? Wnn is equal to Qn. That is W44. N value is 4. That is W44 is equal to Q4, which is nothing but 1. R44 is equal to 0. C44 is equal to 0. We completed almost half of the table. Now by this loop, we completed almost half of the table. Let us see the table. Here see this table, W00, W01. Here we computed W00, W01, W11, W12, W22, W23, W33, W34, W44. We computed all those values from that for loop. Now we need to find these values. By finding these values, we can construct the optimal binary search tree. How to find these values? Let us see how to find these values. I am going to explain. Now let us see how to find these values. For m is equal to 2 to n. Now let us see. For m is equal to 2 to n is 4. N value is 4. 2 to 4. And for I is equal to 0 to n minus m. Here I value is based on m value. I value is based on m value. So first I am taking m is equal to 2. Here m takes 3 values. Those 3 values are 2, 3, 4. First I am taking m is equal to 2. Now in this case I is equal to 0 to n minus m. N is 4, m is 2. 4 minus 2, 2. Now how many values I takes? 3 values. Those 3 values are 0, 1, 2. 0, 1, 2. So first I am going to solve m is equal to 2, I is equal to 0. M is equal to 2, I is equal to 0. Now in this case j is equal to I plus m. What is I? 0 plus m is 2, which is nothing but 2. Here j value is 2. What is wij? I is 0, j is 2. W02 is equal to wij minus 1, w01 plus qj, which is nothing but q2 plus pj, which is nothing but p2. Now here what is w01? We already calculated w01, which is nothing but 8. 8 plus what is the value of q2? Here we have the value of q2. What is q2? 1. And P2 also we need. So here P2 value is 3, Q2 value is 1. Now I am going to substitute those values. Q2 value is 1, P2 value is 3. 8 plus 3, 11 plus 1, which is nothing but 12. That is W02 value is 12. Now here you can see W02 value is 12. Now after that, how to calculate C02 and R02? Let us see. I am going to find C02 value. Now how to calculate that C02? Here we are given K is a value of L in the range such that Rij minus 1 less than or equal to L less than or equal to Ri plus 1 j. Here first we need to take Rij minus 1 and Ri plus 1 j. Within this range we need to consider one L value. Now that L value should minimize the cost. That L value should minimize the cost. Now first let us see how to select those values. Ij minus 1. What is I? 0. I is 0 and j minus 1. J is 2, j minus 1 is 1. R01 less than or equal to L less than or equal to Ri plus 1 j. I plus 1. I is 0, I plus 1 means 1. J means 2. Now let us take these values. R01. What is R01? 1 less than or equal to L less than or equal to R12. R12 is 2. Now that is L is lies between 1 and 2 or it may be equal to 1 and 2. Since L is an integer, we need to consider L is equal to 1 or L is equal to 2. Now which L value I have to take as K? Which L value I have to take as K? Which gives the minimum cost, that is to be selected. Now I am going to find the cost. Corresponding to this L, what becomes the cost? Ci L minus 1. C 0. L minus 1 is 0 plus Cij. C I is 0. J is 2. Now what is C00? 0 plus C02. What is C02? 19. So which is equal to 19. And coming to this L value, C I L minus 1. I is 0, L minus 1 is 1 plus C I J. What is I? I is 0 and J is, sorry, here this becomes LJ. LJ. C I L minus 1. L minus 1 is 0. C LJ and C12. Here what is C12? C12 is 7. So here we get 7. Here we get 7. C LJ 2, 2. Now C01. What is C01? 8 plus C22 is 0. This gives 8. Here this gives 7 and this gives 8. Here you remember this. This is not I. This is L. C LJ. Okay, right. Here since this gives minimum value, here we need to consider K as 1. We need to consider k as 1. So here what is cost of ij? Wij. Here I already calculated wij, which is nothing but cost of ij, that is 02 is equal to w02, which is nothing but 12 plus, and cost of, we got the minimum cost that we calculated. Here the minimum cost that we calculated is 7. 12 plus 7, which is nothing but 19. Here cost of 02 is 19. Now what is R02? R02 is equal to K. What is the K L value we are considering? 1. L value is 1. That is we are considering. So K becomes that L value. So that is 1. R02 is 1. So here R02 value is 1. In the same way, here m is equal to 2, I is equal to 0 I have taken. In the same way you can calculate m is equal to 2, I is equal to 1, m is equal to 2, I is equal to 2. You will get these two cases. In these two cases you can calculate some other values. In the same way you can go for the next m value 3. In that case I value becomes 0, 1. That is you will get another 3 cases. M is equal to 3, I is equal to 0, m is equal to 3, I is equal to 1. Next if you take m is equal to 4, in that case you will get m is equal to 4, I is equal to 0. So you are getting how many cases? 5 cases. In each of these 5 cases you are going to calculate the remaining 5 values, these values. These remaining 5 values. Here I already calculated all these values in the first for loop, and now I calculated this value with the remaining cases. By following the same procedure you can calculate all these values. Okay, now how to construct optimal binary search tree after calculating all these values. Now let us see that process. Here this is the procedure to construct optimal binary search tree. Now let us see, first we are going to take the last value, which is nothing but R04. In the table, what the last value that we are considering? R04, whose value is 2. So here let us take that value R04. Now R04 value is 2 and here K is equal to 2. Now let us take R04 means I is 0, J is 4. R04 means I is 0, J is 4. That is here I is 0, J is 4. Now what is K? What the R04 value is, that itself becomes K. That is K is equal to 2. Now here we take K minus 1 and K. Why we are taking K minus 1 and K only? If you observe the algorithm, in finding the cost we used K minus 1 and K. See I K minus 1, K J. So in between I and J we are considering K minus 1 and K. So that's why we need to take the same thing. So K minus 1 K. What is K? 2. K minus 1 means 1. K means 2. That is we are going to divide this into one left subtree, this into right subtree. So here R01 becomes the left subtree and R24 becomes the right subtree. Now coming to this one, here I is 0, J is 1 and R01 value is 1, that itself becomes K. Now what is that one? I, J, 0, 1, K minus 1, K is 1, K minus 1 is 0 and K is 1. This is considered as left subtree and this is considered as right subtree. So R00 and R11. 00 is left subtree, 11 is right subtree. Now let us consider this one. Now I is 2, J is 4. I is 2, J is 4. K minus 1. R24 value itself becomes K value. K minus 1 is 2, K is 3. So this is left subtree and this is right subtree. So R22, R34, R22 and R34. Here we are getting these two. Now for this, if you go for this, I is 3 and J is 4. I is 3 and J is 4. R34 value is 4. That itself becomes K value. Now I K minus 1 Kj. Here K minus 1 is 3, K is 4. This is left subtree and this is right subtree. R33 and R44. Now these values R00, R11, R22, R33, R44. These values indicates the dummy nodes. Those values indicates dummy nodes. The remaining values indicates key nodes. Now let us see the key nodes. R0 value, 04 value is 2. So the second key element, which is nothing but if. Here we are given key values as do, if, int, while. The second key is if. So if becomes the root node. And here this one R01, which is 1, the first key element do, this becomes the left child. And here this value 3, which becomes the right child. And this value, whose value is 4, this becomes the last right subchild. Now here these are the dummy values. What the values that I am getting? These are the dummy values, dummy nodes. Okay, this is R00, R0, R11, R22, R33, R44. Okay, so this gives your tree structure, optimal binary search tree for the given identifiers. I hope you all understood how to draw the optimal binary search tree for the given identifiers with the given probabilities. Now I am going to summarize the concepts what we explained in this session. In this session we explained about binary tree, binary search tree, why we are considering that binary search tree. Also we explained about optimal binary search tree and how to calculate the search time for the given binary search tree and how to decide the optimal binary search tree. And also we seen the dynamic programming algorithm for solving optimal binary search tree problem, and also we solved an example problem. To assess yourself, here I given some questions. Answer these questions. The first question is, a binary tree is option A tree has one node, option B a tree has more than one node, option C a tree has at most 2 childs, option D none. The next question is, which of the following incorrect related to binary search trees? Option A binary search tree is a binary tree. Option B, in binary search tree all left childs are less than root node. Option C, in binary search tree all right childs are greater than root node. Option D, in binary search tree all right childs are less than root node. The next question is, use function OBST to compute Wij, Rij and Cij values for the given set of identifiers with the given probabilities. Here I given a set of identifiers which are nothing but count, float, if, while. Here I given 4 identifiers, count, float, if, while, and their probabilities also I given P of 1, P of 2, P of 3 and P of 4, and also given the dummy probabilities Q of 0, Q of 1, Q of 2, Q of 3 and Q of 4. You need to find the table, what the values of weight, root and cost of the binary search tree, and also you need to construct optimal binary search tree with the given identifiers. In preparing this presentation, I used the digital content from various public sources. This is only used for educational purpose and not for the commercial purposes. Thank you for listening the session.